I'm not sure what's going on with Zoom, but let me try this again. All right, sorry about that. I think we left off. Here. We left off with this example here. I said we were gonna warm up with this today. We're still talking about retrosynthesis of alcohols that are made from granular addition. So let's take D. And we're gonna go through, I think, had some people chime in on Friday before we logged out, just talking about the ways that we could break this down. All right. So we take this and let's say we take, we're gonna go, we said there were 3 different routes. It asked for 3 different ways to do it. Let's take the first route. What's my first step here? If I'm using this fragment as my green, what's my first step?
To remove the hydrogen.
Anybody? If I'm working backwards, but I'm going to use the highlighted fragment as my green. What's my first step? Is that right? Don't I always have to get back to intermediate?
Dr. Russell, did you not hear me?
No.
Oh, I said remove the hydrogen.
I got you. Okay. Thank you. I didn't hear you. I think my volume may have been down though. My apologies for that. Yes. Now what? If I want to remove this fragment, what's next?
You're going to push the arrow off to the carbon.
This one, like that, you're saying?
Yes.
Mm-hmm. Right, so it's going to leave me with a ketone. That looks like that, plus that, plus that, right? And we know that these two eventually end up as a green, as your ringer. All right, what about the other fragment? Keep in mind the first step in the retrosynthesis or retrosynthetic analysis for these compounds is always the same thing, right? It's right here. That doesn't change, right? You always want to get back to the intermediate, and then from the intermediate, you can figure out what your ketone is and what your granular is. How do I know that I'm going to get a ketone as one of my start materials based on what the product is?
It's tertiary.
Tertiary, good. So I want to get this piece right here. What do I need to do? It doesn't change. This is just reinforcement. It's intended to be repetitive.
You push off the oxygen and push the CH3 also.
Right, that doesn't change. It's going to be the same no matter what. It just depends on what fragment you want. So now this is my ketone. Plus that's negative, plus that. You just marry these two, turn them into a granular. All right. And then here, that's my intermediate. But now I'm looking to remove the ring, because remember, a granular can be aerial, it can be alkyl, or it can be vinyl, right? There are other types of granules too. But it can be aerial, alkyl, vinyl, it can be allylic. It just depends on what you need and what you're trying to do. So here is going to be the same thing. I'm going to do this, where I end up with this as my ketone, plus this, plus that, right? And those two end up together as a granular. Like that. All right. Any questions about the retrosynthesis? I think we've done enough of that to kind of have a gist of what to expect. Are there any questions about that? All right, let me I'm going to assign this one to you to do on your own. Let me upload the new handout. I think I mentioned it in the email that what we were going to be doing, but I didn't realize that the link in the assignments tab wasn't visible yet. So I'm going to upload the handout here, and then I'll also attach it when I send out the announcement for today. All right, so that I just put a PDF in the chat for the next section, which we're going to start now. So if there are no other questions on retrosynthesis, we're going to take an initial foray into substitution and elimination. And I'm going to give you an overview, and then I'll send you some videos this afternoon to reinforce what we discussed today. And then we're going to hit this until the end of the week, wherever we stop. that's the part that'll be on the exam. And then if we need to push part of it to the next exam, that's fine. But we will take the second exam is going to be on Friday. It's going to be the same layout as far as being hosted on Blackboard, but I'm not certain about the proctoring part yet. I'm not certain if I want to use responders or some other method. But yeah, so let's do that. Let's switch gears and talk about substitution and elimination. And I need to put a blank page in so I can give you an introduction. All right, let's do that. All right, so we've actually seen a lot of a lot of both of these already. We just haven't identified it. I think we talked some about substitution when we were doing alcohol conversion to alkyl halides. And I think we also talked some about substitution when we were doing elimination, even just a second ago, those retrosyntheses where you have to put the pi bond back between carbon and oxygen. That's an example of elimination. But let's talk about this in terms of what we're going to be looking for as we study substitution and elimination. So you probably remember from part 1, there were 4 types of reactions, right? There was substitution. I think I asked this before too. Substitution, elimination, addition, and then rearrangement. Right, so with substitution, let's go back to a familiar example. So let's go back to, let's do, all right, so here we had, let's say we had a secondary alcohol. And with that alcohol, we treat it with HCl. You know, that works best for tertiary, but it also works for secondary, just a little bit slower. So if that's the case, right, we get this. Right, and this, because of the nature of the carbon being secondary, right, the substitution can happen one of 2 ways, right? If the leaving group leaves first and we end up with a carbocation, and then that's what chlorine attacks. Right, we can say that this substitution happened. I think we talked about this already. I'm just refreshing you. So we can say that it was SN1. Right, every substitution is going to involve 2 things, right? It's going to involve loss of a leaving group, so every substitution is going to involve a loss of leaving group, which in most cases is going to be the rate determining step. That's going to be the slow step in any substitution, is the loss of your leaving group, right? And it's going to involve nucleophilic attack, right? So for this example, You lose your leaving group, and then the nucleophile, in this case, is chlorine, right? It's going to attack that carbocation. All right. If the chlorine attacks directly, right? If it attacks directly, then it will be considered an SN2 type substitution. We talked about this before. This is concerted. SN1 is stepwise. I think we also even talked about the stereochemistry and everything, right? But at any rate, you're going to get the same product. That you would from the SN1. The difference is if it's direct attack, then it's also what we call stereo specific. Anybody remember what I mean by that? Remember we talked about the inversion of stereochemistry, right? So if it's direct attack, you're going to get, and this is not a chiral center, by the way. So I'm just bringing that up, but it doesn't apply to this example. So you're going to get right, you're going to get inversion, and then over here, right, if it's an SN1 type, then you'll get a racemic mixture. Right, so that's for substitution. Loss of leaving group is the rate determining step. It can happen either by direct attack or by in a stepwise fashion. It's going to be stereo specific. And then the other part that's really important for substitution is the solvent. Right, so if it is, you have two types of solvents. We talked about this in passing, talking about the Grignard. And when we talked about solvents being either protic or aprotic. So protic solvents, protic solvents are going to favor SN1. And if it's aprotic, it's going to favor SN2. We'll talk more about that when we get to it. Are any questions about the substitution? All right, when we talk about elimination, we've seen some examples of elimination, but not direct elimination. So elimination is one of the ways one of the hallmarks of elimination is that you always generate a pi bond. Now I say pi bond on purpose because a triple bond, if you went from a double to a triple bond, that would also be an example of an elimination, but it's not a double bond, right? So I don't want to just limit it to double bonds, right? When you do an elimination, it can be a pi bond. I mean, you can be eliminating to make a double bond. You could be eliminating to make a triple bond. It just depends, right? But elimination also has two pathways. So I'm going to use the same example. Right, and I'm going to protonate it with some acid source so I can make that OH a better leaving group. Now that's positive, right? And then Let me make this into some acid. Let's say acetic acid. All right. This, again, when we talk about elimination, we're talking about putting in a double bond or pi bond somewhere in this molecule, right? So the elimination is going to happen here. It can happen on both sides, but we're just going to pick a side, right? These protons are what we call alpha protons. In any elimination, those are the protons that get removed in the process. So these are, and they're adjacent to your leaving group. Just like substitution, every elimination is going to involve the loss of a leaving group. And it's going to be the rate determining step. All eliminations will involve loss of leaving group. You can't eliminate without losing a leaving group, right? If the leaving group leaves first, this is identical to the SM1 pathway. Only difference is what the outcome is going to be. So if the leaving group leaves first, it's going to be what we call E1. And you're going to get a carbocation intermediate. So leaving group leaves first, it's E1. Right? This is not the elimination part though. That's just the loss of leaving group to give me a carbocation. The elimination happens here, where I take this alpha proton and I grab it and use those electrons in that CH bond to make my pi bond. So now this is my elimination product plus that, right? Anybody not see that? So the water that left can also act as a base in this case and facilitate the elimination. Now, there are other ways to discuss this as well, because you could also have the conjugate base from the acid that we started with do that. Any questions about that? So in the leaving group, just like SM1, when the leaving group leaves first, then you have a carbocation intermediate, and that intermediate gives up an alpha proton, and that's when the elimination happens. Right now, if I took this and I added in a strong base like KOH, now I'm gonna redraw these. That plus and that, right? So if I use a base, anytime you're using a strong base, it's understood that this is E2 elimination. Strong bases are necessary to do elimination in an E2 fashion. Right, so then with E2, it's a little bit different because it is, if the E1, if you notice, this is stepwise. The E2 is going to be concerted. And this matters when we start talking about the rate and all of that other stuff like that. It matters when we're determining the rate law, and there are a lot of other implications for that. But at any rate, this is coming here. This is coming here, and this is coming here, right? So I'm losing my leaving group and forming the pi bond and doing proton transfer all at the same time. Right, so that law, everything is all happening at once. And then obviously when I'm going to get the same product, it's just a different mechanism to get to it. So I'm going to have this with a pi bond plus water plus actually I have two waters. Plus potassium. Questions about that? So for your elimination and substitution, your slow step is the same for both, loss of leaving group. The difference is with a substitution, you're replacing the leaving group with a nucleophile. Elimination, you are kicking out the nucleophile by forming a pi bond. All right, any questions about elimination or substitution? All right, so let's go to here. We'll talk about some of the other factors that affect substitution and elimination. Right, so the first example here is for SN2, and these are all the, we're going to just cover the high points of the different factors that affect the mechanism. Right, this is going to be on this is very important, on a primary or a secondary carbon. And the solvent has to be a protein. And we're going to talk about those two things using, we'll use the top example, right? And if you, again, in the chat, I put the handout, I'm going to upload it again because there's a list in here in the handout that has the different types of solvents. So it's got a protic, all of that's in that handout. So without going through the mechanism, I'll just put another page in so we can talk about the mechanism, the approach of the nucleophile. I think I showed you that before, but I'll show you again, and why the aprotic solvent is necessary. Without going through it, if it's a substitution, what I want to do is identify my substrate, which is this part right here. I want to identify my leaving group, right? And this is my nucleophile. These are all the pieces of this reaction. So you got a nucleophile that's going to react with a substrate to replace the leaving group. And then my solvent is usually here over the arrow, right? Most of the times when you see a reaction written out, the conditions for the reaction are over the arrow or under it. And then you can have the reagents on top and then the conditions under it, right? So with the substrate, what I'm looking for, because a lot of this comes up a lot, having taught this class for so long, it's always the same question. How do I know where to put the nucleophile, where it's going to attack? I'm always looking for the most polarized bond. Right? So there's a dipole here between carbon and bromine. So that's gonna, and this carbon is partially positive, bromine is partially negative. So I always look for that partially positive carbon to know where my nucleophile is gonna attack, right? So without going through the arrows, we'll do that on another page. What's the outcome of this reaction if it's a substitution? Because a substitution is exactly what the name says. I'm taking the substrate and the leaving group, and I'm going to replace that leaving group with whatever nucleophile I'm reacting it with. So in this case, my nucleophile is that methyl sulfide anion, and I'm going to react that with the substrate over here. What is the outcome? Anybody?
A new carbon-carbon bond,
Well, in this case,
or
am I making a bond? So sulfur has the electrons. So the
Oh.
bond is going to be there between that and carbon. I agree you're going to get a new bond, but it won't be between two carbons because the sulfur is what's nucleophilic.
okay, so the sulfur and the bromine will switch.
They switch places, yes. So they do this. Plus Br minus. All right. Now I want to talk about the arrows. So I'm just going to add in a page. So we'll talk about the arrows as well as the solvent being aprotic. So this is my substrate. And then this is my nucleophile. And normally, don't panic, like if you see this in another format or in another book or in another example, if you see a counter ion with this sulfur, so like a sodium or potassium, because that nucleophile doesn't just exist as a negatively charged sodium. There's always some counter ion there to balance it out. Usually it's sodium, sometimes it could be potassium, sometimes it could be another type. It could be an ammonium ion, but it's always going to be a cation, some type of cation to balance that out. All right. So this is the reaction. We've seen the outcome already. Right. What happens in this case, I'm going to try to draw this in, I guess, in 2D. Right. So let's say my bromine is sticking out here, and then there's a hydrogen coming back here. Right. What happens in this case is the sulfur is going to attack here on the backside. Right. That's one of the key characteristics of an SN2. I think I told you this already when we were looking at those alcohol conversions to alkyl halides. Your nucleophile is always going to attack the opposite side of where your leaving group is. And that's going to be due to sterics, right? It doesn't want to come from the same side because it's going to end up bumping into, for lack of a better expression, bumping into your leaving group. And that's going to raise the energy of the reaction, the overall reaction energy, and that's not good. Right, so that's coming there, and then I'm losing my leaving group at the same time. Right, so it's all concerted, and that's how I get to here. And again, this is not chiral. I'm just showing this with a wedge and a dash so you can understand the actual nucleophile coming opposite of where that bromine is. It'll never come from the same side. All right. So that's that. So that means that in the transition state of a SN2, because this is important, right? There's a partially formed bond between sulfur and carbon. And there's going to be a partially broken bond between carbon and bromine. Let me get this back to. Let me clean that up. That'd be BR right there. And then the sulfur is coming in opposite to that, right? So this is partially negative. This is also partially negative because it's leaving with a pair of electrons. So this is a that's partially formed, and this is partially broken. Right, so this is what the transition state for that reaction will look like. And all of your SN2 reactions have a similar transition state. You got an incoming nucleophile and an exiting leaving group. And everything is happening at the same time. Partially formed bond with the nucleophile, partially broken bond with your leaving group. Right? This also matters for the SN2. It matters in the sense of the rate law, which we don't have time. We'll have to do that on Wednesday. But the rate law, and we're going to talk about the solvent, why aprotic solvents are actually necessary. And it's the aprotic solvent is necessary because of the nucleophile. Right? All of this is a consequence of this being concerted. So we'll talk about that on Wednesday. We got to stop right now. Got to get out of town. Any questions about anything before I turn the screen or stop sharing and log out? Any questions?
No, sir.